Okay, so thank you very much. So before I start, I want to ask if there are questions. So far we've said some number of things about the black hole and Hawking's original paradox, and we've said something to resolve one version of the paradox. So on this side we had the bullet points from the lecture uh, uh, 2 days ago, where we said that just doing quantum field theory in curved space time about a black hole background is possible. There are some simplifications that come from the classical geometry, which is what we emphasized here. Then we said they allow us to do quantum field theory in this background. Doing quantum field theory in this background leads to a spectrum that looks like a thermal spectrum for the outgoing particles. And if you kind of keep following your nose, you might be led to the conclusion that a black hole formed from collapse, even if it starts in any kind of a pure state, will always end up in a thermal state that looks like it's independent of the details of what formed it, except for the total mass. And then, we did today some statistical argument where we said that, look, this kind of an argument is not enough to really lead to a paradox, because if you do, typical pure states and microcanonical mixed states are the same for any observation up to order e to the minus s by 2. And therefore, Hawking's calculation is not precise enough to lead to a paradox. However, we emphasized here that, saying that pure states and mixed states are close means that for most observations, in fact, I'd written something incorrectly. I think I'd written typical observations. For most observations, these states are close, and close doesn't mean closed system or anything like that. It just means they're close. They give you numerically similar answers. But the states are not close as states in the Hilbert space. So if you really computed the distance in the Hilbert space between the two states, that's order 1. That's a big distance. So this is what we have said so far. I hope that's conceptually clear, even if the details of all the calculations were not so clear. This on this part of the board is really textbook material. You'll find it in lots of textbooks that have to do with quantum field theory in curved spacetime. This part is not quite textbook material, although it's pretty standard. This review that I mentioned at the beginning, lessons from the information paradox, has these calculations and will also give you references to the original literature and other implications where this is being discussed. So now I'm going to go on to talk about slightly newer stuff, which might be a little less familiar. But before I do that, are there any questions about what we have here or what we have here? Okay, no questions makes me worry a little bit because I it would be very surprising if all of this is completely clear to all of you. Huh? Okay, fine. Let's try effect. Okay, good. Okay. Okay. Uh, okay. So I'm now going to go on and actually talk about slightly more refined versions of the paradox. So in fact, I started thinking about these issues maybe in 2013 or something, and at least for several years till maybe 2018 or 19, I don't remember exactly when. I also thought that if you looked at Hawking's original paradox, this is how Hawking framed it. Okay. And then there were other newer interesting things which people were talking about in firewalls and so on. But in fact, it was only kind of maybe I should have, but it was only then that I went back and I looked at Hawking's original paper. And in fact, this is not how he framed the paradox. Okay? So I now want to explain how Hawking framed the paradox. This is how the paradox is often framed in the popular literature, as I said, and even in physics talks. But Hawking, in fact, had a slightly more sophisticated argument, which I now want to explain. Okay? So what Hawking said was the following. And the paper to look at is a paper on breakdown of predictability from gravitational collapse. It's a famous paper by Hawking. It's called I don't remember the exact title, but it's breakdown of predictability either in or due to gravitational collapse, maybe in gravitational collapse. Okay, fine. Okay, anyway, so you should go look at this paper and look at the argument in the paper. And the argument is not this argument that look, I mean, he says this, that look, the radiation is thermal, but then he tries to come up with a slightly better argument for why it is that these small corrections will not unitorize the radiation. Okay, and his argument is really the following. Let's go back to the Penrose diagram that we drew on the first day. And so the Penrose diagram we drew on the first day had some matter that came from here. and then there's the horizon. Okay, and this is the infalling matter. And what so this is not what I'm now about to say is not exactly how Hawking framed it, but I'm going to translate some of what he said into slightly more modern terminology. Now imagine that you have a Cauchy slice running through this space time. So Cauchy slice is just a space-like slice, and these space-like slices always end at spatial infinity. Okay, this is called spatial infinity on this Penrose diagram. This kind of slice is called a nice slice. When I first started reading the literature, I thought nice slice sounds like something fancy. And sometimes you open papers and they'll say, they'll try and make it, they'll try and write some equations. But really, nice slice is a pretty simple concept. It's the fact that you look at this geometry, and this geometry has some regions of high curvature, which are near the singularity. And it has this horizon, and that's not a region of high curvature if this black hole is large enough. And so a nice slice is just a Cauchy slice that stays away from a region of high curvature everywhere. Okay, so it's a slice of, like the slice I've drawn. It doesn't go close to the singularity anywhere. Okay. So is it clear? This is what this nice slice means. It just means an initial Cauchy slice, just a space, spatial surface that and which doesn't go anywhere in a region of high curvature. Okay? And that's what's called a nice slice. Nice slice is just a term that's used. It's not something that's very deep. So you should. A very nice slice is not a term that's used, but you're welcome to coin it by this thing. Yeah. So, yeah. Okay. So, okay. So this is called a nice slice. And what Hawking said is the following: that look, you can specify data on the past, on the far past. Let's specify data in the far past. And on the far past, you can define a Hilbert space. In fact, by the end of this lecture, I'll explain how these operators and Hilbert spaces are defined at null infinity. But in the far past, you can define a Hilbert space. Let's call it H in. Then he said, look at the slice in the future. Look at this nice slice. This nice slice has two parts. Let's call this H out. And the phrase he used for this was H hidden, but let's use the same phrase, okay? It's hidden because it's kind of behind the horizon, okay? And the division between these is made here at the point where the nice slice crosses the horizon, okay? So what we're using here is the fact that if you take a quantum field theory and you take a Cauchy slice and you divide the Cauchy slice into two parts, then you can write the algebra of operators as a product of an algebra on this side and an algebra on this side. Now, what I said is actually a slightly subtle point, because in fact, to write this product, you have to do a regularization. You have to, if you don't do a regularization, if you go to an algebraic quantum field theorist and you say you're doing this, they'll start objecting that the Hilbert space is not a direct product. But that's actually not a very physical point. Physically, you can think of a quantum field theory and think of a lattice regularization of a quantum field theory. And then the Hilbert space, you can write in a quantum field theory as a direct product of the hidden Hilbert space and the out Hilbert space. Is this point clear to you, at least intuitively, or is it not clear? Maybe it's not clear to many of you. Okay, it's not clear to me. You see, what is a quantum field theory doing? A quantum field theory you can think of as a field that, you can think of as a field that lives on space-time point, on a space-time lattice. Okay. So in space-time, you have various points. Let's call them x0, x1, x2, x3, and so on, up to some, xn, where this is the last point that you have. And then you have various times. So let's call them t0, t1, t2, and so on. Okay. Now, because this is a system where, imagine this is an isolated system, right? And if you give me data about the fields on the initial time surface or on any time surface, that's enough to specify the state completely. Is this clear to everyone? This is just a statement of quantum mechanics. If I give you the state at one time, that specifies the state at all times. So now what are the degrees of freedom on one such spatial slice? Well, there's a field that lives at every point. So there's phi of x0, phi of x1, phi of x2, phi of x3, and so on, right? And then there's up to phi of xn. So if you think of the set of all observables, you can write the set of all observables as a product of observables from this side. So let's say I draw a line now in the middle. That's exactly that blue point. Let's say I divide this in some way, in any way that I like. I divide into two parts. Let's say I make the division at x2. Okay. So then the product of observables becomes a product of observables from this side. Like all observables can be written in terms of observables on this side and observables on this side. And you can check that the Hilbert space itself can be thought of as the direct product of excitations from this side and excitations from this side. Okay. That's because, what is the Hilbert space? The Hilbert space consists of, you can think of the Hilbert space as breaking up into harmonic oscillators, right? And you can think of the Hilbert space as breaking up into harmonic oscillators. And so the set of all states you can think of as the set of all excitations that belong to this Hilbert space. I'll use the same notation. Let's call this H hidden. Here there's nothing hidden. And let's call this H out. What did I call it? H out. Yeah. And so the Hilbert space of the theory factorizes as a tensor product into a part on the left of this line and a part on the right of this line. Okay? You can make such division in any surface. As long as you write down some surface that divides the Cauchy slice into two parts, the Hilbert space factorizes into a part on the left and a part on the right. Is it now clear why this happens? The fact that there's entanglement doesn't have to do with the tensor product factorization of the Hilbert space. When we write down a Hilbert space of 2 qubits, that that Hilbert space is factorized into a space of 1 qubit and a space of the other qubit. There might be some states which are not factorized, but that doesn't mean that the Hilbert space is not factorized. So entanglement tells you that there are some states which are not factorized. If you think of the space of 2 qubits, that space is factorized. This is the basis. This is a 4-dimensional space. And this actually factorizes into a product of a 2-dimensional space and a 2-dimensional space. Okay. Now, there might be states which don't factorize, which can't be written as a direct product of a state from here and here. That doesn't mean the Hilbert space doesn't factorize. The Hilbert space is by definition a tensor product. That's why the space of n qubits has dimension 2 to the n. Okay. So the Hilbert space factorizes. You can think of it this way. The way you can think of a field theory as a set of qubits. It's not really a qubit if it's a field. If it's a fermionic field, maybe you can really think of it as a qubit at every point. And then it's the Hilbert space factorizes. Okay, is this clear? Yeah. The time evolution is unitary here in this quantum in this setup, but the factorization of the Hilbert space is an even more basic property. Is it possible that time may evolve differently? It is possible that time may evolve differently. The factorization of the Hilbert space doesn't make much reference to time evolution because the Hilbert space you define it in instant of time. So if you have a Cauchy slice, and it's a much more basic kinematic property of quantum field theories, which is that if you have a Cauchy slice, the degrees of freedom break up into degrees of freedom on one side and degrees of freedom on the other side. And then, maybe things evolve in whatever way they do, but the factorization of the Hilbert space is really much more basic. It's the statement, these are the degrees of freedom. So this is a property of qubit or spin chains, also quantum field theories. Okay. Now, it's going to turn out that this is not going to be correct for theories of gravity. Okay, so as I said at the beginning, one reason we study the information paradox is because it teaches us something about gravity. And so it's going to turn out that this kind of factorization is not going to be correct for gravity in a very fundamental way. Okay, this is not going to be true, but we'll come to that. But for now, I'm explaining the argument that Hawking made. So Hawking said, look, this is the Hilbert space here. And so the time evolution, whatever it is, must map, this space to some hidden space times an out space. Okay. Then Hawking said, look, there's some calculation that I did which showed that the state in this out space is given by looking at the states of these outgoing modes. Okay? In fact, these outgoing modes are the things that specify data on this on the outside of what's happening. So he said, look, I did some calculation that said that the states of these outgoing modes are thermal. However, let's say you come and tell me that your calculation is not precise enough, which is what we've written here, right? So you did some calculation. So let's say we were to go and tell Hawking. Hawking anticipated this, but let's say we go and tell Hawking that, look, your calculation is not precise enough to lead to a paradox because you wrote down this calculation of these thermal states, but these thermal states, in the end was could be corrected by small corrections, and if you did that, then you would have concluded that the space outside or the state outside was a pure state. It was not a mixed state. What Hawking said is fine. Maybe my calculation has small corrections, But notice that the state outside, to get the state outside, you have to trace over the state inside. So, to get the state outside, to get the density matrix outside, what you have to do is take the full state and you have to trace over the over this hidden sector, which is the part which is behind the horizon. And look, because you are tracing over the hidden sector, and because you expect that there will be entanglement between the outside and the inside, therefore the state that you will get outside will be mixed. Okay. This process is what Hawking called the principle of ignorance. Okay. Well, no, it's the principle of ignorance. This is actually what appears in the abstract. Okay. The reason it's called the principle of ignorance is because the observer outside is ignorant about what the state inside is. Okay. And in fact, Hawking said, look, what does the observer outside know about the state inside? Okay. So, when you do this trace, you have to be a little careful. So, what Hawking said is, the observer outside only knows about the mass, charge, and angular momentum. Outside only knows M, Q, and L inside. Okay. So, in fact, this trace is not really an unrestricted trace. Even in Hawking's original paper, this trace is not really an unrestricted trace. It's a trace with respect to a given fixed mass, charge, and angular momentum. So, what Hawking said is you need to do a trace of inside, but the trace that you do inside, by the way, you will not find this equation in Hawking's paper, okay? You'll find words in Hawking's paper. But what Hawking said was the principle of ignorance tells us that the observer outside can only measure the mass, charge, and angular momentum of what is inside and is ignorant about what's happening outside. That's the statement that in a theory of gravity, even in classical gravity, you have to be a little careful about this factorization. Because it's not really true that the degrees of freedom inside and outside are independent, even in a theory of classical gravity. Because if you put some mass inside, that mass inside can be measured here. And similarly, the charge and the angular momentum inside can be measured outside because you can do a Gaussian integral and measure that. So it's not really true. Like we are already seeing that if you draw this qubit picture that I was drawing earlier, the factorization that occurs there is somewhat different from what occurs in gravity. But what Hawking said is, well, okay, but you have these three numbers, but apart from these three numbers, which you have to keep fixed, you have to trace over all possible configurations of the interior. And that's what he called the principle of ignorance. And if you do that, well, you'll get a mixed state. And therefore, if you look at the state outside or the state on Scri plus, this is called Scri plus, then the interior of the black hole, where it evaporates, kind of vanishes, it goes away. Therefore, all that is left is the state that's outside. The state inside goes away. All that's left at late times is whatever the state outside was. And this process tells us that even if this evolution is unitary, if you look at the full evolution, then that evolution is just an evolution from the space inside to the space outside. And this is not unitary because it takes a pure state here to a mixed state here. Okay. So this is a refinement of the paradox saying that, we are not, earlier what we were saying was that, there's a particular state on H out, which is the state given by that calculation. Now what Hawking is saying is fine. You don't believe my calculation or you think it can have small corrections, fine. But look, you draw this nice slice. This is so in fact, he said this is a basic property of quantum mechanics. It's not really a property of quantum mechanics. It's a property of locality. He said, look, it's a feature of quantum mechanics that the Hilbert space must factorize into inside and outside. And therefore, you have to trace over the inside. When you trace over the inside, true, there are some constraints like the mass, charge, and angular momentum. You keep those into account. You still have many possible configurations inside that give you the same mass, charge, and angular momentum. Therefore, you get a mixed state. So, there's an assumption also here, which is that you have many states which give the same observables outside. Okay, this is the assumption. So because of this is some non-trivial trace, and when you do that, you'll get a mixed state outside. Okay. Okay, so is this argument clear? This argument, I haven't written down too many equations because there aren't too many equations that go along with this argument. But that's the argument. Is the argument clear? Yeah. So do you see how this is an improvement on the original argument? Because the original argument was trying to say, look, there is a specific state outside, which is a thermal state as computed by quantum field theory in curved spacetime. This argument is saying, fine, maybe it's not that state, maybe it's some other state, but it's still a mixed state because you still have to do this trace, and there are so many configurations inside which give rise to the same observables outside. When you do the trace, you'll get a mixed state outside. Okay, so that's a refinement of Hawking's paradox, and it crucially involved this principle of ignorance. Okay, so I don't know how to summarize this quite in a bullet point. I'm just going to write a bullet point, which is principle of ignorance, which you should keep in mind. Yeah. In the meantime, why don't you think about this argument and see if you can reconstruct it for yourself? I'm sure some of you will have questions, and this is actually a good time to have some discussion if there are questions about this. So we are going to, as I said, what we are going to now do is somewhat unfamiliar. So you should stop and ask me more questions. Yeah. Yeah, good. So that is indeed one resolution of the paradox, which is that the information kind of remains inside. Okay, and it remains inside, although that's not. There's some problems with that. That's one possible thing to say, which is that look, when the black hole. I'm going to come back. I'll come back to this question. Let me just write the bullet point, and I'll come back. Yeah. So that's a good question, and I'm going to come back to that. What this is bullet point number 8 or something, whatever. Principle of ignorance. Okay. So this is the bullet point that I just made, which is that, if you assume this principle of ignorance, which basically means you can do a trace, and there are some other assumptions, there are many configurations inside, and the assumption of the factorization of the Hilbert space suggests that the state outside is mixed. Now the question is that you asked was, well, why did I say that this hidden state goes away in the end of black hole evaporation? So it's possible that the hidden state doesn't go away, and that's what's sometimes called a remnant scenario. Okay, where so what happens is, it's clear the black hole becomes smaller and smaller. It clearly loses energy. Right? So you could ask, can it still keep a lot of states inside? Can it still keep a lot of information as it loses energy? You see, because if this hidden state is going to actually not disappear, and it's going to somehow preserve information so as to purify this state, the dimension of this state is large, right? Because there's all this Hawking radiation that's coming out. So therefore, the hidden state must have a lot of internal states. But when the black hole has almost evaporated away completely, that means that even in that small black hole that remains, so that small stuff that remains, there are still a lot of potential internal states. Such a scenario is sometimes called a remnant scenario, where the hidden state doesn't actually vanish away, but rather what happens is that the black hole evaporates, but the information of what is inside always just remains inside. And you have all these different possibilities for all this information about the infalling matter is kind of stored inside. So even if you start with a very big black hole, you let it evaporate, you trust this argument of Hawking for a long time. But however big the black hole that you started with, the place where you start believing that maybe evaporation stops is when the black hole comes close to the Planck scale. So at that point, the evaporation of the black hole, you can say, stops, because we don't know how to do the calculation because some quantum effects become large. But remember, the stopping point of the evaporation is always the same regardless of what the starting point was. Even if you started with a black hole that was 10 to the 100 times Planck mass, the stopping point is always near Planck mass. So somehow it must be that this Planck mass size objects actually can have a lot of possible internal states. Such a scenario is called a remnant scenario. Such a scenario runs into different problems because it seems to spoil effective field theory. one kind of argument that's often given is that such a scenario would, let's say you are scattering some particles, let's say 2 gravitons. Okay. And remember, the way we are supposed to do loop computations is you're supposed to calculate sum over. I'm giving a this is a rough argument. So say this is graviton 1, graviton 2 going to 3, 4. Okay. And you do some loop calculation in the middle. Now, when you do this loop calculation in the middle, you're supposed to sum over all kinds of particles that can run in the loop. But if you have all these remnants, which have a huge number of possible internal states, then what will happen is when you sum over all of these possibilities, you will get a huge factor that comes from the fact that these remnants, even though they might be very high energy, so maybe there's some big cost to producing them as virtual particles. And in fact, you can estimate how much the cost is. If the mass of this remnant is m and the distance over which they propagate is r, okay, then this virtual process is suppressed by e to the minus mr. Okay, because the mass is m and the process and the distance is r. So if the size of these particles is r, so they're kind of produced and they annihilate as fast as they can. Then this kind of process is suppressed by e to the minus mr. On the other hand, if there are e to the s possible states, then this kind of process is enhanced by e to the s. Okay. Now for a black hole, you can check s is actually mr. S, you can check this, that s is actually mass into the radius. It's always true in all dimensions, in fact. Okay, that the entropy is in fact given by m into r. However, if for this remnant, what you would have you'd have a mass which would be Planck mass, a radius which would be Planck radius, but you would have an s which would be arbitrarily large. Therefore, the contribution of these remnants in internal processes would be very large. And therefore, these kinds of remnants would spoil the scattering of ordinary gravitons. Like if you scattered ordinary gravitons, you would find big corrections coming from the fact that there are so many virtual particles that can run in loops. Okay. This is the argument that's usually given to rule out the scenario that you mentioned, which is that the hidden sector can't continue to exist for arbitrarily late times. Now, there are some people who say, well, this argument is not watertight. It's not watertight. It's kind of a rough argument. But you should know this argument. So this thing you said is an important point. It's the story of the remnant scenario. And that's the usual argument that's given against the remnant scenario. Yeah.
So, in general, the theory CBT have a unitary assumption like classical mechanics or quantum mechanics. We do not usually have the principle of ignorance giving the structure of those things.
No, we do.
We have a principle of ignorance.
We do. Principle of ignorance is actually just, in modern language, just saying you do a trace. It is just the fact that if you give me data on this side and you don't give me that data, then I have to do a trace subject to whatever constraints are. So what Hawking said is that at that time, maybe, I don't know, maybe trace over subsect of the Hilbert space wasn't so well established. But principle of ignorance really means you do trace. We do traces all the time. We do partial traces all the time. So
information overall.
No. Partial trace. Sorry. The partial trace is just being done because you're saying that this inside sector is going to vanish. It's not going to be there. So you'll only have the part outside. Because you'll only have the part outside, all this information is going to be lost. That's why it's called information loss. Look, here's a big hidden sector. It's all going to go away. And what you're going to get is just going to be the Hilbert space outside. Therefore, you trace over what's inside and you will be left with a mixed state outside. No. For other type of tracing scenarios, you don't throw away the hidden sector. What's happening here is the hidden sector is going to go into black hole evaporation, is going to, So usually, you don't say that's loss of unitarity. You just say you didn't keep track of those degrees of freedom. Here, it looks like the hidden sector is going to vanish. Okay. So is this argument clear? Yeah. It's an argument. It isn't like you can make this very precise. In fact, as I'm going to say now, this argument is in the end going to be wrong. But I think this argument tells us something interesting. And I think that what I'm now about to explain is that I think one of the most interesting things we learn is that this is not true. Okay. This trace actually is not something that makes sense if you really think of the full theory. This trace is not something that makes sense. And this assumption that the Hilbert space factorizes in this way is not going to be correct, as I'm now about to explain. And I think that's one of the interesting things we learn about gravity. And it's something that's true in gravity independent of black holes. It's not a feature of black holes. It's just a feature of gravity. But I'll come to that. But is this argument clear? Yeah. Okay. So now I'm about to say something which is a feature of gravity, which is I'm about to say Is this point also clear about remnants? Hope is this point okay? Are there any other questions about this argument? Okay. So now I'm about to make a different point. Okay, I'm again, as I said, as I did in the morning, I'm going to just say some things about gravity, and I'm going to spend some time discussing some features of gravity, and then we'll come back and discuss the paradox. Okay, so as I said, as I was doing in the morning when I was discussing how close are pure states to mixed states, that was just a result in statistical mechanics, which is good for you to know anyway. So, as I said at the beginning also of these lectures, in the end, why do we study the information paradox? It's not an empirically important paradox. It's not like black holes in our universe are evaporating and we're worried about loss of unitarity. They're not even evaporating. The black holes that we know in our universe, in fact, are absorbing the cosmic microwave background. And the time of evaporation is much larger than the time of evaporation of the universe. Sorry, than the lifetime of the universe. Therefore, it's not the time of evaporation of the universe, than the lifetime of the universe. Yeah. So, this is not a paradox that's empirically important. However, by thinking about it, you're forced to learn various aspects of quantum mechanics and gravity and other things, which are interesting in their own right. So, one of the things we discussed today about the statistical closeness of pure and mixed states is a result in statistical mechanics, which is just interesting in its own right. Okay. Similarly, tomorrow we'll discuss the page curve, which is also a result in quantum information, which is just interesting in its own right, which came out of thinking of black holes. This result also, in the end, came out of thinking of black holes. Of course, you could have said anyone could have derived it earlier. Right? It's not a hard result to derive, but in the end, it came by thinking about black holes. And what I'm about to say now also came by thinking about black holes, but it's an interesting result in its own right. Okay, so I'm now going to discuss a different feature of gravity, and I'm about to say in gravity, we don't have the principle of ignorance. Okay, instead, I'm going to say we have the principle of holography of information. I'll explain what that term means. What happened? And the statement is that in a theory of gravity, okay, I'm going to make a strong statement and then we'll spend about maybe this lecture and some part of tomorrow's lecture trying to understand it in various ways. That if you give me a compact region, if you look at observables in the complement of a compact region or a complement of a bounded region, and I have to make all of these statements more precise, which we will do at least in one case, are sufficient to specify the state completely. Okay, what does this mean? Okay, so I'm now going to say some words about why you should what this means, and then I'm going to try and explain why physically you might expect this to be true, and then we'll try and prove this in one simple example, in one simple case, and then we'll come back to why it's relevant for the paradox. But this is anyway a property that's true of gravity. And the statement is that imagine you have some Cauchy slice. Okay, so everything here is on Cauchy slices. So when I speak of bounded region, I'm speaking of a bounded region of a Cauchy slice. So for instance, this region is a bounded region of a Cauchy slice. Bounded just means it's bounded, doesn't go off to infinity. Okay? So statement is if you look at observables in the complement of a bounded region, that's observables in this R bar. So this is a bounded region R. This is a complement of a bounded region. Then observables in the complement of a bounded region are sufficient to completely specify the state. Okay, that's a very surprising statement. If you think about it, it is not true in a quantum field theory that observables in the complement of a bounded region are sufficient to specify the state. In fact, the example I drew of qubits, where I showed you qubits at different points in space, it is not true in that case that if I give you observables in the complement of a bounded region, they're sufficient to specify the state. You can see it's just manifestly not true that if I have a slice, this means you take a bounded region and take everything else except for that region. That's the complement of a bounded region. Right? So if I give you a slice, remember this is the same figure that I was drawing earlier. x2, x3, x4, whatever, up to xn. Let me take this region. This region is a bounded region, the region that contains x2, x3, x4. Right? Now, the region x2, x3, x4 is a bounded region because it's these three dots. And the complement of the bounded region is everything, is all points x except for x2, x3, x4. So, now it is simply not the case that if I give you observables on x0, x1 and x5 up to xn, that they also determine the values of observables in x2, x3, x4. You see this? For an ordinary quantum field, it's not true, right? Because you have some fields that are living here, which are living at these lattice points. If I tell you the value of this field, how will you know the value of this field? You won't. Right? So if I tell you the value of this field and all other fields, but I throw away the values of these fields, there's no way you're going to be able to get the values of these fields. So it's not true in an ordinary quantum field theory that observables in the complement of a bounded region determine what's happening in the region. So is it clear that this statement, if it's true, is a very special statement about gravity? It cannot be true in a theory which is not gravitational. Okay? Is this clear? Yeah.
If that statement is true, does it matter what the nature of the state is, whether it's pure or mixed?
No. Well, okay. Okay, good. So, yes, actually, that's a good question. So, no, it does matter what the nature of the state is. Here, I'm assuming that the whole state is pure. If the state on the whole slice is pure, then it's true that then the statement holds. Actually, that's a good question. If the statement is if the state is mixed, then of course you can't determine the state completely by giving me observables in a bounded region, because if the state is if the gravitational theory is entangled with some other degrees of freedom that are not in the gravitational theory itself, then it would not be true. So it's true that this is true in a pure state. You're right. Let me add this. By pure state, I mean the whole state is pure. Okay. So, if the statement, you see, I first want to emphasize that such a statement, if it's true, is certainly a very surprising statement. It would not be true in a quantum field theory. Is this clear, this point? Okay, good. Now, you might ask me, why should you even believe that something like this would be true in gravity? Yeah. Of which point? That it's in a pure state? Well, the whole thing. Yeah. So the whole system is in a pure state. The whole system is not entangled with something. What do you know? What's the significance of the point? It means that maybe I'm not understanding the question. What I'm saying is that, let's say I imagine I take that quantum field and I put the whole system in a pure state. Then it's not true in a quantum field theory that if you give me observables in all the lattice points excluding x2, x3, x4, that I can determine observables in x2, x3, x4, right? You see that? Because they're independent observables. If I have a qubit chain, I have a spin chain. You can think of spin chain. And I give you all the spins except for these 3 spins. And you can't determine the values of these spins, right? Is this correct? You cannot, no? If I give you values of all spins except. So, what I'm saying in gravity is that that's not like that. In gravity, if I give you all the observables outside this room, they're sufficient to also determine what's happening inside the room. Well, right now I'm just saying it's a statement, it's a true statement about gravity. Why we need that, we'll discuss. But I'm saying it's a true statement about gravity that I'm about to explain. But if it's true, you see, it's a very surprising statement about gravity, right? It would tell you that gravity stores quantum information in a way that's very different from other quantum field theories. So it's a very deep statement about gravity if it's true. Exactly. So that's how we want to apply it. If you know the observables outside the black hole, they're in fact complete. You don't need to know things inside the black hole. They also determine what's happening inside the black hole. Something when that's fallen into black hole by looking at what's happening outside. That's right. That's what. Yeah. Okay, but right now we are not saying anything about black holes. I'm just making a statement about observables in the theory of gravity. So all I want to say is that if you look at observables in the theory of gravity, the observables in the complement of a bounded region are sufficient to completely determine observables in the region itself. And what I've explained there is that this would not be true in an ordinary quantum field theory. Okay, good. Now, you would ask me, why should you even believe that something like this would be true in a theory of gravity? Right? So first I want to give you some physical intuition. Okay. So the first thing to realize is that there is a property, such a property that in fact we already discussed earlier, which has to do with the Gauss law. Okay. The first feature is that you have the Gauss law. You see, the Gauss law already tells you that there is some dependence between observables inside a bounded region and observables outside a bounded region. Why does it tell you that? Let's say I told you that you could make, let's say we're just thinking of classical gravity. Okay, forget about quantum gravity. I told you, I'm not telling you what's happening in the room, but I'll let you make measurements outside the room. Okay? Then I can already say what is the total mass of all the people in the room. You see that? Because I'll take the gravitational flux, I'll integrate it on the walls of the room. By doing that, I won't know, how many men, how many women. I won't know that. I won't know, how many younger people, how many older people. I won't know that, but I'll at least know the total mass of all the people in the room. So you see that in gravity, there is already at least something, even in classical gravity, there's something that's already unusual, which is that the Gauss law tells you that if you have, degrees of freedom in the room, then the total energy is determined by what's happening outside. Do you see that already? And that's already different from the kinds of constraints that occur in any other theory. That's already different from the kinds of constraints that occur in this qubit system. In these qubit systems, where we like to think of how quantum information is stored, there are no such constraints that say that measurements on this qubit and this qubit can determine what's happening here. Okay? Now, I also want to point out a difference between electromagnetism and what's happening here. If you think of electromagnetism, you might think there's a Gauss law there as well, and you can determine the total charge. This is true. However, there's an important difference between charge and mass, which is that the charge can be both positive and negative, whereas the mass can't be negative. So if I tell you that in electromagnetism, tell me how many electrons there are in the room, you actually cannot tell me how many electrons there are in the room, because an electron and a proton together have zero charge. What you can tell me is how many excess electrons there are, but you can't actually tell me how many electrons there are. However, in the theory of gravity, I'm just pointing out, you already have an unusual feature where you have a charge that's always positive that can be measured at long distances. So this is already telling you that there's something unusual about gravity. Do you all of you agree with this? Okay. Let me make one point which might already, which might be confusing later. So I'll make it now. Okay. Forget about quantum gravity. Let's just think of classical gravity. Okay. So how do we know the mass of the sun? Right. This is the sun, and this is us. None of us have ever been to the sun, right? But we know the mass of the sun because we know the gravitational field of the sun, right? We can see the gravitational field. We know it's spherically symmetric, so we know the mass of the sun. And so we know what the mass of the sun is, right? It's 2 into 10 to the 30 kg. Let's say the mass of the sun were to change by half suddenly. Half of the mass of the sun suddenly goes away. Then it seems that the Gauss law tells us we would know about it instantaneously because the integral of the gravitational flux should change. How is that consistent with causality? It's not. So what happens then? So what will happen?
We have to know about it later.
Is that so? So if the mass of the sun, let's say half of the mass of the sun just vanishes. So what will happen? There, we have this equation, right? Which is integral g dot. So this is the gravitational field dot n hat dA is equal to m, and I can never get the. So this is the gravitational field. Let's call it small g, and there are factors of g Newton and so on. But let's forget about them. Yeah, we have this equation. No, let's put the vector here. Okay, so this equation stops holding for some time, or what happens? Then what happens? I think in Newtonian barely is to J, but in general, the field has a propagation speed. Okay, so in general relativity, this is actually still a very important equation because in general relativity, this gives you the definition of what's called the ADM mass. So in general relativity, there is a very similar equation. It's in fact the definition of energy. If you open Misnath-Hall and Wheeler, you will find that the definition of energy in general relativity is almost defined by taking the gravitational flux in a region where the field is weak and by integrating it. Like that's how you define the mass in a region. You go to a region where things are flat or close to flat space, you integrate the gravitational flux, and that is how the ADM mass is defined. So this equation certainly holds also in general relativity. The question is a bit of a trick question, by the way. So it's not the question is there's something wrong in the question. So that's a hint.
Yeah. not formalize it at the time.
It's not formalized in terms of time. No, it's a simpler trick actually. So the question is, if the mass of the sun decreases by half, like half the sun just disappears, then what will happen? Will this equation stop holding for some time? It will not hold for 8 minutes. After 8 minutes, it will start holding again. Or what will happen? Is that what will happen, or is it just something, or will we know about it instantaneously, or what?
Not
After 8 minutes. So for 8 minutes, this equation will not be true. No, sun's not. Yeah, yeah. Okay, okay. Let me stop. There's a trick here. The trick is that the mass of the sun cannot vanish. Okay, if in gravity, energy momentum is conserved locally. Okay, so this question is wrong. If someone asks you the question and says, "What if the mass of the sun decreased by half?" It's not possible for the mass of the sun to decrease by half. The only way the mass of the sun can decrease by half is if some matter is ejected from the sun. Right. So you have the sun here, right, and this is us. So the only way the mass of the sun can decrease is if some matter actually goes through here. And of course, when it goes through here, there's no complication with causality because the mass actually exited the Gaussian sphere. So the only way the mass can decrease or increase is by actually physically exiting the Gaussian sphere. And that's also why there's no contradiction with causality with the fact that we know what the mass of the sun is now. Why do we know what the mass of the sun is? Because the mass of the sun came from here in the past. That's how you have to imagine states are formed. That in the past, the mass of the sun kind of entered from where we are, from infinity. And when it entered, it left a memory. I'm using the word memory here in a loose sense. People who study gravitational fields discuss memory in a different sense. Here, I'm just saying memory in a loose sense, in that it kind of modified the metric, and that metric is what we are measuring now. That metric which was modified when the mass of the sun left. And this equation is always true. And it's so the mass of the sun cannot decrease by half. If someone asks a question that's a wrong question, it can only decrease by half by the sun ejecting some mass. And when it does that, then of course there's no problem. The metric where you are will change. Okay? So everything is local. This equation is completely consistent with causality, even though it suggests that an observation here knows about what's happening here. Okay, so I would be many times when we talk about this, when we'll say something about quantum gravity, people will ask this question about when I'm not what I'm now about to say, but how what I'm now about to say is consistent with causality. But if you have such a question in this at the end of this lecture or tomorrow's lecture, you should remember what we have just discussed, which is just a statement about the classical Gauss law. In the classical Gauss law, a set of observations here know about what's happening inside, and they know about what's happening inside not by any violation of causality, but because the matter came from infinity, and the only way it can exit is now by going out to infinity again. Okay? So it's more that, if you draw this on a diagram, on a Penrose diagram, we are kind of here, and the matter came from here, and we are kind of here. And so we are here, and the sun is here. And so, where we are is actually it's separated from the instantaneous position of the sun, but it's not separated from the past world line of the sun. So the Gaussian surface is never separated from the past world line of the sun. Okay. So is this clear at this point? Okay, good. So what have I said so far? What I said so far is that there's an unusual property of quantum gravity, which I'm going to claim. And the only thing I've said so far is, look, you should already realize there's something unusual about gravity, which is even in classical gravity, there's a Gauss law which tells you this. Okay. Now this cannot be the full story, clearly, right? It can't be the full story because apart from the Gauss law, all of you are probably also familiar with Birkhoff's theorem. Are you familiar with Birkhoff's theorem? Birkhoff's theorem tells you that if you look at a spherically symmetric distribution of matter, then the metric outside is the same. Regardless of, it only depends on the mass, regardless of what the distribution of matter is. Okay? There's a similar theorem that you can prove in Newtonian gravity also. You've probably proved this theorem, which is if you take some ball of dust and you look at the gravitational field outside. In fact, the way it's proved is often by taking this equation and by using the Gaussian surface to compute what the gravitational field is. Let's say you take a spherically symmetric distribution of matter and you compute what the gravitational field outside is. Then, you assume there's spherical symmetry, and the gravitational field is therefore m by 4 pi r or m by r squared. Okay, and it's m by r squared and it doesn't care of what the density of m is inside. Okay, so when you're inside, it matters, but when you're outside, it doesn't matter if the Earth becomes, the sun, for instance, can increase or decrease its density without changing the gravitational field outside to the extent there's spherical symmetry, because that only depends on the total mass. Okay? So in classical gravity, it is not true that observables in the complement of a bounded region are sufficient to specify the state in the region. In a classical gravitational theory, this would not be true. Right? You see, it would not be true because in a classical gravitational theory, there are important observables here which have to do with the density of the sun and other reorientations you can make in the sun, which cannot be captured by just looking at the mass outside. And this is, in fact, what Hawking had in mind. Hawking was, of course, aware of this. But Hawking said, look, there are so many, if you fix the total mass, there are still so many possible internal configurations that you can have. Mm. Okay. However, I now want to point out that there's another important property which comes from quantum mechanics. And now what I'm going to give you is just an argument. What I'm now about to say is not a proof. So if you have questions, you should keep those questions. We'll try and discuss them more, which is the uncertainty principle. You know, imagine that I have some operator, okay, that changes the configuration of the sun from one configuration which has one mass to another configuration which has exactly the same mass. There are such operators, right? So there are operators which take you from one energy eigenstate to another energy eigenstate. Such an operator is an operator which has zero energy by definition, because it's taking you from one state which has some energy to another state which also has the same energy. Okay. Now remember that in quantum mechanics, if you look at some, so what I'm saying right now is a little is not very precise. So please take it just as intuition. What I'm about to say now, I'm just trying to give you intuition for why this might be true. In quantum mechanics, remember, if you think of some excitation, then if this excitation is bounded in position space, then this excitation necessarily has some fluctuations in momentum space. So if you think of some excitation that has zero energy, okay, means also has zero momentum or zero, then such an excitation must necessarily be integrated over all of space. If you think of some excitation of a system that has no energy, then such an excitation must necessarily be delocalized. So if you think of an operator that can change the configuration of the sun from one configuration with a given mass to another configuration with a given mass, the uncertainty principle suggests that such an operator must be delocalized. Okay. Therefore, if you do an operation that changes the sun from one mass to another mass in such a way so as to keep this total integral constant, then you must change some other observable outside the sun. Okay. So suggests that operations. So this suggests that yeah. Sail to commute. Okay, what I've written here is that if you think of operators that keep the mass fixed, so that they keep this integral fixed, then such operators must fail to commute with some other operators at infinity, because they must be infinitely delocalized. These two things together suggest that, if you fix not just the mass, but you also fix other operators, other observables at infinity. If you fix the energy and other observables, not just the energy, if you fix the energy and other observables at infinity, that suggests, what I've said right now is not a proof, but it suggests that you fix completely the state of the interior as well. So these two things suggest, I emphasize they only suggest that fixing H plus other observables at infinity or fixes the state. Okay. So notice that there are two things that went into this. One is that the energy was fixed by a Gauss law and it could be measured outside in this region R bar. And second, that operators which change the energy, which change the state without changing the energy, must necessarily be delocalized. So they must leave some other imprint on this region R bar. You cannot have an operator that's completely localized to R, but that changes the state of R from one state with a given energy to another state with the same energy, but is completely localized to R and therefore commutes with all operators outside R. Okay, that comes from the uncertainty principle. So these two things are meant to give you intuition for why something like this should be true. Okay? And as I said, something like this is, one can show that it is true, and it's a very interesting thing we learn about gravity, okay, which we'll apply to the paradox, but it's true in general. Okay, is this intuition clear? What I said right now is not a proof. So the intuition is twofold. First, you have the Gauss law, which tells you can measure the energy. In classical gravity, that's not sufficient because you can change configurations. Like I can change, a proton with a proton plus an electron with a neutron or whatever, keep the mass fixed. But an operator that does that in quantum mechanics will have to fail to commute with something else because it must be delocalized. Okay, these two things suggest that fixing the energy plus other observables, not just the energy, fixes also the state inside. Yeah. That state will be. Well, it'll be whatever the state is. So the whole system we're assuming is in a pure state, but fixes the state, meaning that it uniquely identifies the state. You cannot have two states which are consistent with the same observations of energy and other observables outside a bounded region. In a quantum field theory, you can. In a quantum field theory, you can have many states which are consistent, which give you the same observations outside a bounded region, but give you different observations inside the bounded region. You see, that was the example I gave in the beginning. If you think of a quantum field theory and throughout 5 degrees of freedom in the middle, and you fix all degrees of freedom outside, nothing you can do can determine what those 5 degrees of freedom in the middle are doing. There are different configurations I can write down, which are consistent with every observation you make outside. What I'm now saying is that in the theory of gravity, this argument, rough physical argument, suggests that this is not true. Okay, is this point clear? Is the intuition clear? Okay. Yeah. Yes.
So what we're saying, right, is that the observation in
Yeah, so if you could write down an operator that commuted with everything outside, so one of the observables outside is the energy. If you could write down an operator that was completely localized to this region and that commuted with all observables outside, then such an operator, of course, would be invisible to the person inside. So let's say you could write down an operator U that commuted with a unitary operator that commuted with all observables in R bar. Then the state psi and the state U psi would give you the same expectation value. So let's say you had a state psi and you have a unitary which is localized to psi. This state psi and this state UR psi give you the same expectation value for all observables in R bar. You see, because you measure some operator in R bar, because this U commutes with all operators in R bar, it would be the same. So if you could find such a unitary, then you would have defeated this argument, right? You would have said, look, I found a unitary, therefore you cannot distinguish between this state and this state. So what I've told you so far is a statement that you cannot find such a unitary. Okay? This statement sometimes goes by the name by saying you do not have gauge invariant local operators in the theory of gravity. So these two statements suggest you don't have gauge invariant local operators. These two statements sometimes go by that result.
the outside of the ethering changing the outside.
We'll tell you everything about the inside is the claim. Yeah, we'll tell you everything about, not something. Something is clear already in the classical theory already. So the statement here is stronger. It'll tell you everything about the inside. Okay. I want to say something about the choice of words here, why it's called holography of information. In string theory, we have precise examples where something like this is true. So one such example is called the ADS-CFT correspondence, which is an example where you think of quantum gravity in an anti-de Sitter space. And in this anti-de Sitter space, it turns out there's a dual theory that lives on the boundary of this anti-de Sitter space. And that dual theory tells you everything that's happening in the bulk of anti-de Sitter space. Okay, this is called holography. Now, what we are going to prove here is going to be slightly weaker. Because we are not actually going to write down a dual dynamics. In these examples where you have ADS-CFT, you have a dynamical dual. You have a situation where you can actually say, if I have this dynamics in the bulk, I can compute some other dynamical quantity on the boundary, which will tell you how the bulk evolves. What we are going to prove here is going to be more along the lines of a kinematic statement. It's going to be a statement saying that there exist observables outside that can determine what's happening inside. But that's different from saying that the observables outside can be reorganized into a dynamical autonomous theory. That would be a more interesting statement. That would be a statement of full holography. What we are saying is a statement which is a weaker statement, which is that these observables outside, we know they exist, or we can show that they exist, but we will not be able to show how you can reorganize them into a dynamical autonomous theory. Okay, that's why it's called holography of information. Not because it's a stronger statement, but because it's a weaker statement than holography. Okay, so is the intuition clear? Now what I'm going to do for the remainder of the lecture today is I'm going to give you an example of where you can see this work in perturbation theory. Okay, and then tomorrow I'll give you a more formal argument, which the formal argument will be phrased in flat space at null infinity, which will try and demonstrate that result. But the formal argument might be hard for everyone to follow. So I'm just going to give you a perturbative example, which I hope all of you will be able to follow, just using ordinary quantum field theory to give you some more intuition. So I give you some physical intuition without writing down any equations here. I'm now going to write down some equations and give you an example of where a situation something like this works. Yeah, and if you can understand the example is not a very strong result because it's going to be a perturbative example, but actually I think it's intuitively very instructive. Okay, so where should I go? Let's go here. Okay. So the example I'm going to give you is the following. Yeah. I'm going to show you, I'll make everything precise, but I'm going to show you, imagine that you're in flat space. Okay. So this is the Minkowski diagram of flat space. Okay. And imagine that, I'll make this whole story more precise. Imagine that some bomb goes off here. And by the way, again, if you can catch where I'm cheating here a little bit, that's extra credit to you. But I'll come back and ask you where I cheated a little bit at the end of this. Okay. Imagine a bomb goes off here. Okay. So a bomb goes off in the middle of flat space, and it sends off some shock wave. Okay. Which goes and hits null infinity. Okay. So it sends off a shock wave or sends off some beam of light. In the calculation we are going to do, we are going to imagine we have a scalar field, which is a massless scalar field, which gets excited by this bomb. Okay. So this bomb goes off, and this is Cry plus, this is Cry minus. Are all of you familiar with the diagram of Minkowski space? And you have something here which goes and hits Minkowski, this boundary of future null infinity. Okay. Okay. Now we have some observers here. Okay. And these observers have to make some measurements here. And by making measurements here, they have to determine what the profile of this wave was. Okay, so I'll make all of this precise. So these observers were here. These observers need to determine the profile of the excitation. Which excitation? This one. Okay. And I'll now make this precise, of this excitation. Okay. So is the problem clear in words? Okay. And you see, in quantum field theory, this is an impossible statement. You see why it's relevant to what we are saying? Because these observers are space-like separated from what's happening here. Right? So how can they determine the profile of this excitation? If these observers were to wait, and they wait till they reach here, then they can determine the profile of the excitation. However, we are going to give these observers detectors which are like Cinderella detectors. I hope all of you have read the story of Cinderella. Now I don't know if people read it. We used to read it when we were growing up. The story of Cinderella was Cinderella had a carriage and so on, but the carriage would turn into a pumpkin at midnight. Okay, so these things, these observers, they have some detectors. What well, good question. No, maybe it's local. The carriage turns into a big pumpkin, the same mass. Yeah. So anyway, these people have some detectors, but their detectors turn into pumpkins here. Okay, at this point, so they can't wait. They can calculate and do whatever they like, but the detectors are going to stop working at this point in null infinity. So they can't actually wait to this time. Okay, so from here to here, they just have pumpkins. They don't have detectors. So they have to determine what's happening here, but they can't wait, right? Because they don't have time to wait. They have to make some measurements here. And you can see in quantum field theory, it would be impossible for an observer here to determine what's happening here, because these points are space-like separated. So how will they determine this? Okay, let me make this more precise. Now this is the problem in words. I'm going to make it more precise. Okay. So let phi, sorry, of E r omega be a massless field. Okay, so this is a massless field. Okay. Okay. Now it's convenient to work in what are called retarded coordinates. Are you familiar with these retarded coordinates, where you go to coordinates which are u is equal to t minus r? The advantage of these retarded coordinates is they are the convenient coordinates to use in null infinity. So instead of using t, let me write u. Okay, all of you familiar with, it doesn't matter if you're familiar or not. Instead of using Minkowski time, I'm going to use this retarded time. This is called retarded time. Okay, it just means you take the Minkowski time and subtract off the radial coordinate. So this is written radial coordinates. This is the angle on the sphere. This is an S2. We in 4 dimensions. So this is the position on the sphere. This is the radial coordinate, and this is t minus r. Okay. Okay. Good. The way you go to null infinity in these coordinates is you take r to infinity while keeping u fixed. Okay. While keeping u fixed. Okay, this is not v. I'm sorry. This is r. Okay, I'm sorry. I can't write an r, but this is r. Yeah, this is everywhere. It's r. Okay, so take r to infinity while keeping u fixed. By doing this, you go to null infinity. In this, what happens to this field, you can check by solving the field equation. Is it goes to 1 over r into O of u omega. Have any of you seen this expansion before? You know, even those of you who haven't or think you haven't, you have probably seen this before, because this kind of asymptotic limit is also what appears when you derive the S matrix from bulk correlation functions in the LSZ formula. Okay. So what I'm saying here is you take this field and you go after r goes to infinity. Okay. If you look at the wave equation for this field, you will find that this field always dies off as 1 over r, and then it has some profile in u and omega. Okay. So I'm writing the field as r goes to infinity in terms of O of u omega and then a 1 over r factor. This operator is said to be intrinsic to Scri plus. It is an operator that's really a boundary operator. It lives here. Okay. This operator is very closely related to the operators that you use to describe the S matrix. For those of you who studied quantum field theory and studied the LSZ formula, the S matrix is defined in terms of some out operators. Okay. This operator is literally the Fourier transform of those out operators, even though the way I have introduced it here is by taking a bulk field and going to r equal to infinity and then looking at the 1 over r coefficient. But for just to say some words for those of you who are familiar with the LSZ formula, this is the Fourier transform of the operators at Scri plus that are called the out operators. For those of you who are not familiar with the LSZ formula, just imagine you have this bulk field, you go to infinity and you define, and you get a 1 over r tail, and the coefficient of that tail I'm calling O of u omega. Okay. This operator is an observable at Scri plus. It's not some observable that's defined at infinity. In theories of gravity and study of gravity, these kinds of observables are very useful. And the reason they're so useful is because these observables don't care about what is happening in the middle at finite r. Okay. These observables are called asymptotic observables. And asymptotic observables are very important in gravity because you see, right now we are not doing fluctuations and so on. Right now we are just doing a case in Minkowski space. But in the case when we go and start talking about black holes, then we'll have a situation where the bulk might be fluctuating. There might be all sorts of things happening at finite r. However, whenever we do quantum gravity, we always keep the asymptotics fixed. We always say asymptotically far away, we are still in Minkowski space. Okay? So when you go very far away, things look like flat space. So this kind of relationship still holds in all these black hole spacetimes and other spacetimes that are called asymptotically flat. That's why even when we prove a precise result, it will always be in terms of these asymptotic observables, not in terms of these bulk observables. Even though bulk observables are useful to develop intuition, this observable at finite r in the theory of gravity is very hard to even define precisely because the bulk is fluctuating, you have to fix gauge and so on. Whereas this is a nice operator, even in the theory of gravity. Okay. Okay, is it clear what this operator is? Okay, now I'm going to quote a result which I don't know how to. I can't. I don't really have time to prove, but I'm going to quote a result, and it's not so hard to derive this result. Okay, do you know the 2-point function of this field is in 4 dimensions? The 2-point function of this field is just 1 over geodesic distance squared in Minkowski space. So phi of u r omega minus phi of the 2-point function of this field is just the geodesic distance squared. If you take that and you push this to r equal to infinity, you will find the following result for the 2-point function of that field, which I'm now going to write down. For some reason, I have the factors of 4 pi and so on correct in my notes. Usually, I've been working in units where 2 is equal to 1, but in this case, I have the 4 pi's written, so I'll write them. Okay. So this is the 2-point function that you get at null infinity. If you take this 2-point function, which is 1 over geodesic distance squared, and you push it off to infinity, then you will find that this field has a 2-point function at null infinity, which has some features that actually you should be familiar with, which often appear when you study light cone physics of this kind. Notice that the field, so this omega is also coordinated null infinity. What is it doing? It's telling you how you go around, right? It's kind of telling you how you go around. That's what omega is doing. I've drawn it in 2 dimensions, but omega is kind of going around, right? Going around. So notice this field at null infinity has correlations only at a given value of omega. There's a delta function in omega that you get. You get delta of omega omega prime. So field at one value of angular coordinate is only correlated with other fields at the same value of angular coordinates, nowhere else. So you get that delta function in omega. And then you get a correlator. So if you just look at the OO correlator, that has some log term. But the del u O correlator has this form which looks like 1 by u prime minus u. The minus I epsilon has to do with the fact that I put this on the left and this on the right. Okay. It's not going to be so important. The 1 over 4 pi is completely unimportant. Okay. Just remember the 1 by u prime minus u into delta to omega omega prime. Yeah, this is all flat metric. We are in Minkowski space. We know the 2-point function. Okay. That result, by the way, is also true even if the metric is not flat. It almost comes from the definition of O. But here I'm asking, you can derive this result by just starting with this 2-point function and just taking R to infinity. Okay. This is a good exercise actually. I think I assigned another exercise in the morning. I forgot and I've forgotten what it is. But this is actually also a good exercise for you to do. It's not an undoable exercise. Take this 2-point function in flat space, just in flat space, write down the 2-point function and take the limit as r goes to, of both points going to infinity. And when you, so define O that way and you will find that 2-point function emerging. Okay. And it's kind of nice to see it emerging. Okay. Okay. So this is the 2-point function that you get for these fields at null infinity. Okay, very good. So now I have to make the story precise. I said some words there. What does this mean? So what it means is the following. What question? The question is prove this. The question, well, this question I'm now making precise. The exercise I'm assigning to you is to prove this. I'm not assigning this as an exercise to you. I'm assigning this is an exercise for me. This is an exercise for you. Okay. So this is the exercise for you to prove this. We start with this 2-point function and prove this. Okay. I'll try and do this exercise. I'll assume you guys have done your jobs. So you've proved this. And I'll do this one. Yeah? It's okay. Okay. So I first have to even make the question precise. Okay. So imagine that you're in the following state. Let me get my factors right since I have the notes. I. Okay. This state is a state where f has support at f of u omega. I'm making the question precise for myself first, okay? So I said there's some bomb that goes off that hits something here. What I'm imagining is you're in that state. Okay? This is a state where I took this field O, yeah, I smeared it with some function f. This function f has support only near u equal to 0, 1. Can someone tell me where u equal to 0 is on this diagram? Yeah, it's the middle. It's actually this line. U equal to 0 is like here, conventionally. You can choose origins wherever, but u equal to 0 is here. It's the point where t is, notice u is t minus r. So u equal to 0 is where t is equal to r. When you draw the Penrose diagram, u equal to 0 is this line, this point. Okay. This point is u equal to minus infinity. This point is what? Yeah. So what is the value of u? Plus infinity, right? So this point is u tends to plus infinity, and this point is u tends to 0. This point is when time is much larger than the radius. This point is when time is much smaller than the radius. You've gone off towards spatial infinity. Okay. So this is like at the edge of the Cauchy slice. This is near spatial infinity. This is near time like infinity, and this is in the middle. Okay. So this bomb I said is going to go and hit this null infinity in the middle, right? So this is near u equal to 0. So this is now the state. I've made it precise. This is the state psi. It looks like e to the I lambda times f of u O of u on the vacuum. So it's it's a unitary, if this is a unitary operator, right? It's a unitary operator that acts on top of the vacuum that looks like it is localized between u equal to 0 to u equal to 1. U equal to 1 is right here. Okay. This f of u is some integral of O, it's a smeared integral, but it's localized, it has support only near u equal to 0 to 1. Okay. Okay, and the task, and now right now I wrote it in words, I'm making it precise. So question is, working to order lambda using correlators in u in minus infinity to minus 1 over epsilon, it determine f of lambda. Okay, so far I just written, let me u prime. So the task, so I said, observers need to determine the profile of this excitation. What that means is that you take the state and you measure some correlators near in u prime in minus infinity to minus 1 over epsilon. Can someone tell me where this region is here? It's this region. Okay. This is minus infinity and minus 1 over epsilon is somewhere here. It's some large negative value. So it's this region here. Okay. So this is where we said our observers can make measurements. Is it clear? So the question is, make some measurements on null infinity, but in this region to determine what the form of f is, even though f is actually here, even though the excitation comes here. Okay. So mathematically, I've now specified the problem completely. It is, you're given this state and you're allowed to measure correlators near minus infinity to minus 1 over epsilon, and you have to determine what f is. Okay, good. Let me first point out that this exercise is impossible in a quantum field theory because this is a unitary operator. Okay, and this kind of a unitary operator, will commute with anything that you write down here. Okay, so in a quantum field theory, if you take that unitary operator and you try and ask, can you measure something here to determine what it is? The answer is no, you can't, because those operators just commute. Okay, good. But now I want to explain why in a theory of gravity, you can in fact determine the form of this f by working here. And it's going to realize the intuition I mentioned earlier about using the Gauss law and the answer to anti-principle. Okay. Okay. So I claim that you need to measure the following correlator. So measure the correlator psi h O of u prime omega prime psi. Okay. So I claim you determine this correlator to order lambda. Remember, u prime is in minus infinity to minus 1 over epsilon. H is the Hamiltonian. Okay. And why can you measure the energy in minus infinity to minus 1 over epsilon? Is because of the Gauss law. Remember, because in a theory of gravity, so this game can only work in gravity. It can't work in quantum field theory. So even though we were working in Minkowski space, we are still going to imagine that at least one property of gravity is true, which is that at least the observers here can measure the energy. So they can measure the energy, but they can measure the energy here. And this is a feature of gravity. The fact that they have to do an integral around this omega sphere, but they don't have to make any local measurement. They can just determine the energy by doing an integral near u equal to minus infinity. You see that? So this operation, this correlator is a correlator in this region, because this insertion of O, which is the same field that we had here, is inserted explicitly for a value of u prime in minus infinity to minus 1 over epsilon. H is explicitly and observable at minus infinity. And I claim that this 2-point function, as I'm now about to show you, will be sufficient to determine this O, this F completely. Okay, so let me just take a step back. If you're getting lost, for some of you might be getting lost because we're using a lot of quantum field theory here. Okay, so I'm going to take a step back and say where we are. So the name, so far, till here I was only saying words. I was saying that look, in a theory of gravity, we have the property that the observables in the complement of a bounded region are sufficient to specify the state completely. And I give you some physical words for why that might be true. And now I'm giving you an example. Okay? The example is that we have a bomb that goes off in the middle of space, and you have some observers here who are only allowed to make measurements here, far away, near infinity. They have to determine what the form of the bomb was, how long did it go off for, what was its volume profile or whatever. That's what they have to determine. So these observers are not allowed to measure things here. Now, because of what is coming tomorrow, I'm making things slightly complicated by framing things in terms of null infinity. So even though this problem was by saying things happen in a Cauchy slice, it will turn out to be more convenient to actually do things in null infinity. And to do that, I said, let this be a massless field. And then I define some limit of this massless field as you took R to infinity, which is an operator at null infinity, which is this operator O. See? The advantage, today there's no advantage of using this operator O. For today, I could have done everything in terms of this field phi. Okay, but the advantage of using the operator O is that it is introducing you to a notion of an asymptotic observable. An asymptotic observable is an observable that you define only at infinity. And the advantage of using such asymptotic observables is that in a theory of gravity, they're well defined even when the bulk is fluctuating. So I said, think of this observable O. In terms of this observable O, I'm now making this bomb state precise. It is the following state. It is this operator O integrated with this function F, put inside a unitary and acting on the vacuum. And I put a parameter lambda just to make life a little easier for myself so I can work in perturbation theory. Okay. So this is now my state. And the name of the game was, this F has support only for u in 0, 1. And to make those words precise, I said working to order lambda. So I can work to first order in lambda. And using correlators only in u prime in minus infinity to, so only using correlators here, determine what the form of F is. So first I want to point out that it's completely obvious that something like this cannot be done in quantum field theory. Because in quantum field theory, this is a unitary operator that commutes with all operators here. So you can never perform that task in quantum field theory. However, in a theory of gravity, I've given you intuition that the Gauss law and the uncertainty principle are useful. And so I said, in a theory of gravity, I will show you that using this 2-point function, which is the energy and the correlator of the energy and this operator O, is going to be sufficient to determine that function F. Okay? And I'll just compute this to order lambda. Okay? So I'm running a little short of time, but if I can go on for 5-10 minutes more, I'll do this calculation and show you how you get an answer. Okay. Okay, good. So let's calculate that too. So I'm now going to do some calculation, which can be, let's do it here. Okay. So let's just calculate that correlator. I'm claiming that this correlator is going to be sufficient. I'm claiming it because I know it's going to be sufficient, but let's just calculate what that correlator is in that state psi up to first order, right? So when we compute that correlator, what do you get? So what you get is 0 e to the minus I lambda integral f of u omega o of u omega. Let's call this u double prime because these are all just dummy variables, yeah? Omega double prime. Then you have an insertion of this h, you have an insertion of o u prime omega prime, and then you have e to the I integral f of u omega O of u omega du d omega acting on 0. Okay, I just written out that correlator. I've just expanded it out. Do you see this? Okay. Now I'll just expand, because I'm working to first order and lambda, I can expand out both sides to first order and lambda. Right? Even though this is a unitary, it's an exponential, I can expand it out. I can do a series expansion in order lambda. Is that fine? That's okay. So this looks like 0 into 1 minus I lambda integral f of u double prime omega double prime O of u double prime. Same thing, h o u prime omega prime. I'm just writing these equations out in detail so you can see how they go. Okay, so I've just expanded both terms out. Okay. Okay, now I have to work to first order in lambda. Now look at this h. Okay? This h acting on this one, acting on this 0 is 0. You see this? So we know that. Let me write here. Or let me write. Where should I write? Somewhere. Okay. So 0h is equal to 0. Because 0h is 0, I can ignore and have to work to first order in lambda. Okay. I have to pick up this term. Because if I don't pick up this term, if I pick up this 1 from here and this lambda from here, I'll get 0. So I have to pick up this term. You see this? So, and I cannot pick up this term then because I only want to work to first order in lambda. You see this? So this correlator to first order in lambda in fact becomes the following correlator. This exercise I'm giving you is an exercise in quantum field theory, so it's a first year graduate exercise, but all of you should be able to do it. So please try and follow this. You will be able to do it. It's not very hard. It becomes just this correlator. Okay. I can erase and write on the board, which is an advantage which you can't, but you have the advantage that you can go on to the next page, which I can't. Yes. Okay. Okay. So this correlator just became this correlator, you see, to first order in lambda. Because the other terms went away. One term was lambda squared and the other term was 0. So this is the only correlator that you have. Yeah. Okay, good. Now I'm going to take this h and I'm going to commute it through this O. Okay. So, you know, this O of u double prime omega double prime on h, this h, is actually equal to h o u double prime omega prime plus I d by d double u double prime O of u double prime omega double prime. Where did this come from? This is the Heisenberg equation of motion for the field. Remember, h generates translations in time and u is just t minus r. So at null infinity, this h generates translations in u, which tells you that the commutator of h with this operator at null infinity is just the derivative of that operator with respect to u prime. Do you see this? So you can commute this h through here. Okay. When you commute this h, you see this term will again give you 0 because this term by that equation there will act on this 0 and so it will give you 0. You see this? When you commute this h through this O, once this h goes to the left, you will get 0. So the only term that remains is this term. You see this? Yeah? Okay. So what remains? So now you can play the same game. So I'm going to erase this h. That minus I will cancel with the plus I. You'll get just a lambda. And you'll get a d by du double prime. And the h is gone now. You see? That's what the 2-point function became. Good. Now somewhere along the way, we had written C. So now, as I said, I was going to rely on you to have done the exercise. If you did this, if you've done this exercise, I mean, you'll do it later, but we have this 2-point function written on the board. You see? It's just a 2-point function of a derivative of O with O. Right? So what do you get for that 2-point function? Well, you just get, notice this omega double prime, which is sitting here, is going to give you a delta function with this omega prime which is sitting here because of that delta function, right? So what will you get? So you will get f of u double prime omega prime divided by, now what are the factors? 1 over 4 pi and this one, okay. U double prime minus u prime plus I epsilon. You get a lambda and a 4 pi. And I might have lost some factors by now of 2, but this is roughly, okay. This is the answer for the 2-point function. And then you have a plus order lambda squared. Okay. So I've done this in some detail, but everything I did, I promise you, is just, a first year quantum field theory exercise. Okay. It's not often taught in quantum field theory textbooks, but I haven't done anything which is not a first year quantum field theory exercise. So I've computed this answer for the 2-point function. Now notice something very nice. This f has support only for u double prime in the region 0 to 1, right? This u prime is actually inserted in the region minus infinity to minus 1 over epsilon. But this 2-point function is non-zero for that value of u prime. It's not 0. In quantum field theory, any 2-point function I measured there would be the same as the vacuum 2-point function. But this 2-point function is sensitive to the value of f. Why did that happen? It happened because the Hamiltonian did not commute with that. This was a result of the Gauss law, the fact that we were being able to pull out the energy. But the energy is just one number. Here we are being able to pull out much more. We found a 2-point function that's sensitive to all aspects of f. And the way you can see that it's sensitive to all aspects of f is just by doing a series expansion. By noticing that this can be written as minus lambda by 4 pi, or let's see, f of u double prime omega prime into u double prime to the power n, sum of n by u prime to the power n plus 1. Let's see. Let's hope I got that correct. I don't know if I got all my minus signs right, but all I did was I did a series expansion of this. So take the u prime and write it as u prime into 1 minus. I think I might have got it right. Okay. All I did was I series expanded this. Why can I do this series expansion? Because remember, this u double prime only goes over 0 to 1. Whereas this u prime is near minus infinity. So the mod of u prime is much larger than the mod of u double prime. So I can do a series expansion u double prime by u prime. And this is just a series expansion of 1 by u double prime minus u prime. Okay. So I just write this as 1 by u prime into 1 minus u double prime by u prime. And then I expand that out in a series. So I get that expression, right? This is not part of the integral. The integral here is only over u prime. So what did I get? I'm sorry, I'm writing just one last thing here and then I won't write any further. I got u prime to the n plus 1 and I have a sum of n over n and I have an integral over u double prime to the power n, f of u double prime omega prime, and the sum goes over n equal to 0 to infinity. Okay. What are these numbers? These are all the moments of f. You see, I'm allowed to make measurements anywhere in u prime in minus infinity to minus 1 over epsilon. So if I measure that correlation function for different values of u prime near minus infinity, I can extract the coefficients of all of u prime to the n plus 1. And these coefficients are just the moments of f. So by doing this, I get all the moments of f. And the angular distribution is completely fixed by the fact that I had the delta function. So if I give you all these numbers for all n, and the reason I can give you all these numbers is because I know, I can make this measurement at these observers are allowed to make the measurements at different values of u prime. So by making the measurements at different values of u prime, they can do a series expansion of the answer in 1 by u prime. And by doing that, they get all the moments of f. And by doing so, they can completely determine what f is. Okay. So this is an example of how these observers, by making measurements here, which you can think of as measurements near the boundary, can determine what's happening here. Okay. The calculation we did was a very simple calculation, but it's already revealing something very interesting. It's a calculation that would only work in a theory of gravity. If I put back the factors of G Newton here, you could have asked why was gravity important. It was important in the fact that this Hamiltonian was proportional to a component of the metric here at infinity with a factor of G Newton. It's because the energy can be measured at infinity by the Gauss law, Okay, but that is only true in the theory of gravity. So this calculation only works in the theory of gravity. And where did we use the uncertainty principle? We use the uncertainty principle in the fact that these excitations, had to be correlated with excitations here. So this is where we use the fact that there were quantum correlations of excitation of this O here and this O here. Okay. So we use both quantum mechanics and gravity. It's a very simple calculation, but you can see already that you're able to play this game that observers here can determine what's happening here. Okay. So it's already showing this very interesting feature of gravity. Okay, now I'm going to ask you a question. Why is this not violating causality? How did these observers here determine this function f, which looked like it was space-like separated? Okay, the hint is we already played this game earlier. Well, okay, but why isn't it violating causality? Look, the bomb went off here. So I could have set off a bomb here in different ways. Maybe I tuned it so it went off for a long time. I had a detonator which was, big or small. How did these people suddenly know what was happening? Okay, the hint is we played this game some time back. What's the answer? No, no. Detectors do turn into pumpkins. That's not the answer. The detectors turn into pumpkins is what we decided. So we insist the detectors turn into pumpkins. The answer is I shouldn't have drawn the diagram this way. If you look at that state, this excitation actually came from minus infinity. Okay, that state is not. There is no such thing as a bomb going off at infinity in the middle of space. It doesn't happen because in gravity, energy is conserved locally. So that state actually involves an excitation that comes from Scry minus and goes to Scry plus. And what is happening here is that these people are able to detect some remnants or some memory of the fact that this excitation came in from infinity in the past. It's the same reason the classical Gauss law doesn't violate causality. Okay, that this excitation had to come from here. So the moment I phrased it by saying a bomb went off in the middle of space, I was already cheating. I did that to make it sound surprising, but really, it's the fact that this excitation came from past infinity, and that's what these people detected. Okay, so I'm going to summarize what I said right now, and then I'll stop. I'm sorry, I'm already over time. The summary was, I said, so what I've said so far is that, Hawking had a, refined the information paradox to say that, even if his calculation wasn't exactly right, you should really do a trace over the interior. Okay? And by doing a trace over the interior, you would get a mixed state in the exterior. Then I started to say we are now starting to question this. We haven't resolved this yet. Okay, we haven't resolved this refinement of the paradox yet. But I started to say that, by thinking carefully about properties of gravity, we find that gravity has an interesting property, which is that observables in the complement of a bounded region determine observables in the region. I have not proved this for you yet, but I have given you an example and I've given you some physical determine the state for pure states. Okay, I have not proved this for you yet, but I told you that you might think this is plausible based on the fact that in the theory of gravity, there is something unusual, which is the Gauss law, which lets you measure energy at infinity, and the uncertainty principle, which in quantum mechanics tells you that something which changes, one state of one energy to another state of another energy must be necessarily delocalized. Therefore, there can't be something that changes the configuration in the bounded region to one configuration of one energy to another configuration of the same energy without affecting something outside the bounded region. And then I gave you an example of a perturbative example. This is a simple example. This is not a set of all states. This doesn't prove these observers can detect everything. But we played this simple game of saying if you look at this class of excitations, then in this class of excitations, I showed you how by making measurements here, which is, as I said, a first year graduate quantum field theory, a little more advanced than what we were doing in the last lecture, but not all of you should be able to reproduce this calculation we did here. You can compute this 2-point function and determine the form of this f, which in quantum field theory would be impossible because this unitary would commute with all operators here. So this calculation, which is a simple calculation, already shows you how gravity has these unusual properties and how you can determine the form of this function f. Okay, this is not enough, of course, to prove this statement. We'll have to prove the statement by making a more complex argument. This is a statement about Minkowski space, but it's meant to give you some intuition for what's happening. Okay, so sorry for going over time. Thank you for your attention. I'll stop.